This is the example of cold temperature that we did, and it's just an ice bath. Here's some of the data that we took for constant temperature of 22.1 degrees Celsius. We did it at various volumes to try to see the average time of reaction, how long it would take. And there's a general trend here of increasing average time of reaction as the volume increases, which is better shown by this graph here, which again, as the amount of hydrogen peroxide that was used in the barrel case was increased, the time of reaction for any trial was higher than the previous one. Now here is another experiment we did with the hydrogen peroxide. But it was at different temperatures that we did this experiment to try to see what effect temperature had on the rate of reaction. And we took down the times, we took our average time, we did the uncertainty, and we made an assumption when we determined the rate that the initial concentration minus the final concentration over the time it took for the reaction to complete was going to be the rate, but we just assumed that the final concentration was going to be 0. And that's how we determined the rates. We took the natural logarithm and we plotted it against 1 over t to get the graph right here. And from this graph, we were able to determine the activation energy and a reaction constant known as K0, which I'll explain in just a little bit. There's the graph right here. Let's see. Okay, there's a slide. I apologize. It was actually supposed to be before that graph. This is the equation started out with. It's just the change in concentration over time is equal to the rate times the rate constant times the concentration of A, where A is hydrogen peroxide. And through some integration and rearranging, also this K, that's what that equals, the K0. I'm sure you've seen that before. And anyway, when you rearrange it, you get what's known as the exponential decay equation, which is that equation right there. And that's basically what we're going to use later on, but the trend line that you saw on the graph is based off this equation right here, where this is the y of the graph, ln of k, which k is right here. And this is the slope, EA over R, that's the slope, and 1 over t is your x, and ln of k0 is going to be your intercept. So when you plot that, you of course, in Excel, you're going to get this right here, as I mentioned, your slope, and you're going to get that right there, your intercept. If I'm multiplying this by negative R, you get an activation energy, and by raising this to the base E, you're going to get K0. And with those two values, that's really all we need from that graph to move on to the next part, which is modeling the rates of reaction at different temperatures. And basically the way I did it, I took 20-second intervals up to 600-second span of time using that equation right there. And I just modeled it, what it would look like. Here's the first one. I did it at 22.1 degrees Celsius. And as time progresses, you see that the concentration of the hydrogen peroxide decreases, obviously. And this was based on that equation I just showed you with all these values calculated into it. Here's the one for 40 degrees Celsius, and you can see that it goes down quicker, and also the concentration is lower. If I were to carry this out a longer span of time, you'd eventually see it hit to 0. And that's for 100. You can see, anyway, at 600 seconds, it's almost at 0 concentration. So temperature definitely makes it go down a lot quicker. And the next experiment was denture tablets and water. Here's a picture of it and a list of some of the ingredients that are in it. It reacts in a similar way to the hydrogen peroxide and the platinum catalyst, only it's got a solid form of hydrogen peroxide in it and a built-in catalyst. Here are the results for different volumes, have an average time and uncertainty. That's plotted here on this scatter plot. You can see the uncertainties represented by the error bars there. Here's some pictures of the reactions that we did, showing the decomposition of the denture tablets in the water in the color change. Here's another experiment we did with multiple quantities of tablets. We did 1, 2, and 3 tablets to see what effect that would have. We also varied the volume of water as before. And this graph here represents the results we got. See, with a higher quantity of tablets, the average time of reaction goes up. And again, the volume, with a higher volume, you're going to see less time of reaction. A few more pictures there of the different volumes. Here's one we did with a constant volume of 150 milliliters varying the temperature, and again, taking down the average time of reaction. And here's a bar chart that represents the time of reaction versus the temperature. And as the temperature is increasing, the average time of reaction is dropping significantly. And there's a big jump here at 40 PUC from 10.5 to 30.8. That's a pretty big jump in temperature, so that's why it's such a large drop. That's why it's not gradual. Here's what the high temperature reaction looked like when we did it. It was on a hot plate with a thermometer. And low temperature reaction was just in an ice bath. The conclusions, the activation energy for that reaction of peroxide was 22 kilojoules per mole with a, I guess it's called a rate constant of 6.047 inverse seconds. The denture tablets reaction, what we found was that reaction time decreases as the temperature or the volume of the solution increases. Recommendations for some further experiments: it would be a good idea to actually have the reaction take place in a vessel where you could monitor the change in pressure throughout the entire reaction, so that you could use the changes in pressure to get the changes in concentration throughout the whole time, which would give you a lot better representation of the rate of reaction than the big assumptions we made had a lot of uncertainty built into them. And also the phenomenon of the color change with the denture tablets, it'd be a good idea to investigate that and see how that relates to the reaction. Thank you. Any questions?
Let's tell people they can get some more pizza if they want it.
You can have more pizza if you like.
Calling somebody, right?